All right, so we're going to talk about the last section of this chapter 16. We're going to focus on the weak base and salts. So let's start with the weak base. As we know, the only weak base that we have talked about so far is ammonia, which is ammonium hydroxide if you prefer. But if you look at the structure of ammonia, we realize that this is nitrogen with the 3 hydrogens, so this is what the formula of ammonia. And from this structure, we understand this lone pair electron can accept H+, so it becomes a base according to the definition of a BL's definition, Bronsted-Lowry. And this lone pair can donate it, so that fits the base from Lewis' definition. But nevertheless, those 3 hydrogen can be replaced by any organic group, which we call them amine. Okay? INE as the suffix. But all of these, because existence of the lone pair here, so they are the weak bases. Since it's a weak base, it should have a Kb. B stands for base, of course. So we can write up a generic base dissociation equation. All right, so here I would like to emphasize this base dissociation equation a little bit. Remember, it's a weak base, right? So if it's base, what should be present as a product? Remember, according to Arrhenius' definition, base must be, you're right, OH minus. So OH minus must be the product. That is something we have to remember. H0 plus must be the product for acid dissociation. OH minus must be a product for base dissociation. Then we should be able to figure out the rest. The reason for that is, once we know the OH minus, so water must be its conjugate acid, because it has to provide H plus to the base. And here comes another pair of conjugates. All right, so Kb is equal to equilibrium concentration of the product cations and anion multiplied divided by the equilibrium concentration of the base. And also we can do the pKb if we want to by taking negative log of Kb. All right, so if you look at Kb here, the greater the value of Kb, the stronger the base it is. It's follow the same trend as we discussed for the strong acid, strong base. Remember, for strong acid, Ka must be greater than 1. Weak acid, Ka must be less than 1. All right, so we just change that to the base. So for strong base, Kb must be greater than 1. Weak base must have the Kb less than 1. Speaking of pKb, it goes to the opposite trend. So that means the smaller the value of pKb, the stronger the base it is. So for weak base, we can have many types of calculation problems. If we have 3 different types of calculation problem for weak acid, we will have the 3 corresponding type of a calculation problem for weak base. Well, just how we can establish our approaches. So as a strategy, just like the weak acid, equilibrium calculation can be performed to determine equilibrium concentrations or pH from Kb and initial concentrations. Sounds familiar? Because if we switch the Kb with the Ka, that is exactly what we have done for the weak acid. So same strategy applied for Kb, of course with a few exceptions. So here is exception. So we're going to use Kb for Ka, we use OH minus for hydronium. Remember, we talk about a base, right? So OH minus must be the product, not H3O plus anymore. If pH is given indicating the equilibrium concentration in the question, we need to convert the pH to the pOH so that we know the equilibrium concentration of OH minus. So we need one more step to get OH minus, not hydronium anymore. The rest of steps will be taken are exactly the same as those for acids. Okay. So this is basically the strategy, how we're going to switch Ka with the Kb, hydronium with the OH minus, pH with the pOH. Now let's look at one example. So in this example, we have ammonia. Remember, ammonia is the only weak base we're going to talk about in our lecture. Unless it has been addressed, this substance is a weak base. If we have something given formula without saying weak base, it has to be ammonia and ammonia only. In this question, we're going to calculate pH, the concentration of all species, like ammonia, ammonium, hydroxide, hydronium, and the percent of dissociation for ammonia. That is something new. Kb is provided. Okay, so here, pH, I'd like to say it one more time. That is for the equilibrium concentration. And the concentration of solution is considered as initial concentration. All right, so both are involved, so we understand that it's going to be an ice table problem. Remember, question wants to get the pH, right? So if we recall, what is the strategy for us to get the pH from a weak solution if Ka and initial concentration known? We first step identify a pair of conjugates. For weak acid and its conjugated base. But this time we talk about the base, right? Weak base. So we find weak base and its conjugate acid. Okay, ammonia is the base, so we add H plus to it, so it's going to be ammonium NH4 plus as its conjugate acid. Okay, so if we think back for the weak acid for this type of calculation problem, and second step is compare Ka against Kw. Same thing, we compare Kb against Kw to determine which base, because remember water is also the base, right? So which base provides the most of OH minus? Okay, since Kb is much greater than Kw, so we understand ammonia dominates in producing OH minus. And third step, as we write up the base dissociation equation of ammonia, remember OH minus must be the product. That is essential, because if we replace the OH minus with hydronium, we got the chemistry wrong. No matter how hard you try the mathematics, that won't bring you any more credit. Okay, so we have to make sure we need to write a correct dissociation equation. All right, so OH minus must be the product because we talk about the base. OH minus is the anion for base. So we have initial concentration before dissociation, and here instead of put plus X on the hydronium for weak base, we put a plus X on the OH minus. And then we figure out the plus X minus X for the rest of the species. And after we get equilibrium concentration or figure out the involving X, we put them into the Kb. Okay, so we replace those concentrations with the numbers and the X's. So this is what we have. Look familiar, right? So we try out 500 rules. For me, I would try out the 500 rules anytime I can get. Okay. So we have initial concentration 0.4 divided by 1.8 times 10 to the negative fifth. So what we got is 22,222. So that number is much greater than 500. That means 500 rule applies. That's a big relief because we can take x away. So we can take this x away. So because x is so small compared to the initial concentration, so we can simply ignore it. All right, so that makes our life much easier because without that x, so calculation would be a lot easier. So we multiply 0.50 on both sides, then take the square root. So we figure out the concentration, equilibrium concentration x is equal to this value. If you recall, x represents equilibrium concentration of hydroxide as well as ammonia, NH4+. Okay. So equilibrium concentration of ammonia here is 0.4 minus 0.00268. So that is equal to 0.397. If we round it up with the 2 sig figs, we find out it's a 0.40. So that means the concentration of ammonia is virtually unchanged. That's a good sign because our approximation stands. Remember, our approximation is x is so small we can ignore the x in our calculation. So that is why we take x away from this quadratic equation. So we can take a square root on both sides. Let's ballpark check this Kb now that we have the equilibrium concentrations of all species. Put them in, that's perfect match. Remember the Kb according to the question is 1.8 times 10⁵. This is what we have. It's perfect match. So we have absolute confidence to say our calculation is good. So let's finish the rest. Because question wants us to figure out hydronium. Why? Because that's what pH is. All right, so hydronium, Kw divided by the equilibrium concentration of hydroxide. So 3.7 times 10⁻12. Take the pH, so we find out pH is 11.43. Makes sense. Because if we have a solution with the pH greater than 7, we call it base. So our calculation supports why we call such a solution as a base. Speaking of percent dissociation, so that's going to be the concentration of ammonia dissociated and divided by the initial concentration of ammonia. We know the initial concentration of ammonia, but how we wound up with this value for the concentration of ammonia dissociated, because this is the amount of ammonia dissociated so that we can have these two. Since they both have the same concentration, so that would be the concentration of ammonia that has been dissociated. All right, so we find out it's about 1/3% for this dissociation. So very little, but yet it makes the pH is much greater than 7. All right. So one other thing I'd like to talk about here, okay, about the base is how we can relate the base with acid, particularly with its conjugated acid. That is important because remember at the beginning of this chapter, when we talk about the acid and the base, and we said, okay, the stronger the base, the weaker the conjugated acid, vice versa. And here I try to show you mathematically how we wound up this conclusion. All right, remember conjugated pair from this definition. Okay, so conjugated base is the formula with the one fewer H plus and one more negative charge. Conjugated acid is something after we add H plus with one more positive charge. So now let's say we have a base, which is B. B stands for base. And we can add a 1H plus to this base to make it conjugate acid. All right, so we got a base and acid. Remember, conjugate acid has no distinction with the rest of acid. Conjugate acid is an acid. Base undergoes base dissociation. Acid undergoes the acid dissociation. So here we go. Base dissociation of a weak base. So we have Kb. And the conjugated acid, since it's an acid, undergoes the acid dissociation. We have Ka there. Now let's see what happens if we add these two reactions together. We realize we can cancel out the B, the base, and also we can cancel out the conjugated acid as well. Let's see what we have left. We got the 2 molecules of water on the left. We have OH minus and hydronium. What's that? It is the autoionization of water. What is the equilibrium constant for such equilibrium? Kw. Remember in previous chapter, when we added 2 reactions together, what are we going to do with the K? We multiply them, so Kw equals to Ka times Kb. That is another one of the most important equations for this chapter, because that equation tells us how this conjugate pair of acid and base are mathematically related. So this equation is very, very, very important. It tells us, okay, so if we have Kb that's large and Ka should be small. Kb is large, meaning that's a strong base, so Ka must be small, so its conjugated acid is weak. If we still have a problem understanding it, okay, so let's put it this way. Remember, for a strong acid, Ka is greater than 1, so let's put 1. So Kb is equal to Kw, which is 10 to the negative 14. It's very small, so its conjugated base is very weak. Remember, this matches the conclusion that we draw in the very beginning of the chapter. Remember, so when we talk about conjugates, the stronger the base, the weaker its conjugated acid. The weaker the acid, the stronger its conjugated base. So this Kw equals to Ka times Kb is the mathematical proof. All right, so there's a whole bunch of derivation of this equation. So pKw equals to Ka times Kb. I'm sorry, Kw equals to Ka times Kb. pKw equals to pKa plus pKb, and so much. Okay, so we need to understand all these equations. To me, all I need to know is this equation, because we should be able to derive the rest. All right, so in this question, question wants us to figure out what is the dissociation of this conjugated base. The acid is a formic acid. So the conjugated base, after we take away of the hydrogen, which is in the first element, so we have, the hydrogen at the last, so we have HCOO minus. And the question also wants us to figure out what the Kb for this formate. And once we know the Kb, we should be able to get pKb quite easy. Ka, by the way, for this formic acid is provided 1.8 times 10 to the negative 4th. So strategy. So what's the strategy for us to do such thing? First thing first, we need to know just how we write up dissociation of a formate. Remember, formate is a conjugate base, right? So formate is a conjugate base. Conjugated base meaning it will produce, you're right, OH minus. So OH minus must be the product in this dissociation equation. And of course, this is conjugated base of a certain conjugate acid to provide H plus. Okay, so OH minus is conjugate acid, must be water. And this is formate, a base. So what is conjugate acid? but add one H plus to it, so we got HCOOH. So this is just how we write up the dissociation equation for a weak base. And for same argument, we can write up the dissociation of a weak acid. The only this time we put H3O plus as a product. All right, so now that we have a base dissociation format, how do we know it? Again, this is the base, right? So this is the base dissociation. So KB, B stands for base. KB equals to this formula. Okay, so what's the value of KB? Because we find out a pair of conjugates. So we have HCOA formic acid and its conjugated base we call formate. And we know the Ka for 1, so Kb times Ka for this pair of conjugates must equal to Kw. So Kb should be solved, which is a 5.6 times 10 to the negative 11. And also question wants us to get pKb, so let's take the negative log, so it's a 10.25. That is pretty much for the weak base. Okay, so there's going to be a quite calculation for weak base. Okay, so I just gave you the various type of calculation problem for weak base, and you can analyze a little bit and find out what is the approach for the weak base by checking out the corresponding approach for weak acid. Remember, we use Kp replace Ka, we use OH minus replace H3O plus. If we know the pH, we have to convert pH to POH before we can get OH minus for its concentration. Okay, now let's move on to our second topic of today's lecture, salt. Before we talk about salt, so let's summarize what we have discussed about acids. Okay, so there has been quite some time. So when we talk about acid, we realize we have 6 strong acids. And the rest of acids should be the weak acid. So all we have to do is memorize what the strong acids are. And for strong acid, as we demonstrated, Ka must be greater than 1. For weak acid, Ka must be less than 1. For the base, we only have one weak base, ammonium hydroxide or ammonia aqueous solution, or anything else that has similar structure or formula with ammonia. For example, instead of 3 H's, so there could be 3 some fancy ones. Okay. And for strong base, okay, so that is going to be the cation of alkali metals or alkaline metals. But I want you guys to pay attention when we deal with the alkaline earth metal, just how many hydroxide it will provide. Okay. So this is something that I want you guys to pay attention here. Speaking of strong base, Kb must be greater than 1. Weak base, Kb must be less than 1. All right. If we can memorize the strong acids and strong bases, so we know what the weak acids or weak bases are. And those things are quite easy for us to memorize. For strong base, hydroxides for the first 2 groups of the elements in the periodic table, except for hydrogen, of course. For strong acids, we got the 3 strong oxo acids and 3 strong binary acids. This is something that we have discussed for some time. So what about salt? So let's take ammonium fluoride as an example. Remember, salt, according to the definition we learned in Chem 1 class, is the product of reacting acid and base. So let's imagine, in order for us to have ammonium fluoride, which is salt, So what would be the reacting acid? Remember, acid must have H. So that would be H plus with an anion, fluoride. What do we got left for the rest of the product? From the rest of the product, NH3. Of course, it's a base. So we can write up the reacting acid and the base for any salt. All right, now, if you look at the cation ammonium, okay, with ammonia, so we realize ammonium cation is a conjugated acid for ammonia. So this is what a cation is. Cation is a conjugated acid for something. And what about anion? Anion is the conjugated base of something. Okay. So these are the two important statements for us to recognize what those cations and anions are. So cations is an acid, conjugated acid of a reacting base. Anion is a base. It's a conjugated base for the reacting acid. All right. So now we have characterized acid and base with strong versus weak. So if we play the combination of acid and base to form salt, so we have 4 different types of salt. So we have acid, salt, yield from strong acid, weak base. SAWB means strong acid, weak base. Salt yielded from weak acid and strong base. Salts yielded from strong acid, strong base, and salts yielded from weak acid, weak base. Let's look at the salt yielded from the weak acid and strong base. Like, for example, baking soda. Everybody understands baking soda is a weak base. If you do not know, now you know it's a weak base. If you look at the formula, it's cation, sodium, with hydrogen carbonate. All right, so how should we be able to figure out this salt that made from strong base and weak acid? So here is my unique approach. Okay, it's very different from what is said in the textbook. Okay, I would like to share with you guys because I think that is quite powerful. It's easy for us to understand. Okay, so here you go. What am I going to do is for cation, remember, cation is what? Conjugated acid for reacting base, right? So we need to figure out what the reacting base is. According to Aaron Neal's definition, base is OH minus. So what am I going to do is, so I'm going to add enough OH minus so that the charge can be balanced. Na plus, 1 plus charge. So I'm going to add 1 OH minus to it. So once charge is balanced, I got a compound we call the base, NaOH. What do you think that is? Strong base or weak base? Strong base. For hydrogen carbonate, it's anion. It's a conjugate base of the reacting acid. So I need to figure out what the reacting acid is. For acid, I'm going to add H plus. 1 minus charge requires only 1 proton, so I'm going to add 1 proton to it to make it H2CO3. What do you think this acid is? Strong or weak? It's a weak. Let me tell you why. Because it's oxo acid, 3 minus 2 is less than 2, so that's a weak acid. Okay, imagine I got 1 mole of strong base giving me 1 mole of OH minus, right? Because it's strong base. And I also have 1 mole of a weak acid, carbonic acid, which does not give me 1 mole of a proton to work with. Remember, this weak acid does not dissociate 100%. So once the reaction is finished, H plus reacted with OH minus, do we have something left? Is that going to be H plus or OH minus? Remember, 1 mole of OH minus means less than 1 mole of H plus. Which one got left? OH minus. OH minus means what? Basic. So that is why we now understand baking soda is basic, because there's a certain basicity left over. Remember, it's a strong base, weak acid. OH minus cannot be completely neutralized. So this is my understanding to judge what kind of salt this one is. If it is a weak acid, strong base, so more base left over, so salt is basic. We can also try this approach with the example of a salt yielded from strong acid and weak base. A good example, ammonium chloride. Ammonium conjugated acid of a reacting base. So how do we get the base? Add OH minus to it, so we have ammonium hydroxide, the only weak base in this class. Cl minus, conjugate base, so we can add H plus to it in order to get a reacting acid, HCl, strong acid. Imagine that it's 1 mole of strong acid, 1 mole of a weak base to react. So I got 1 mole of H plus. How many moles of OH minus? I do not know, but I know for sure it's less than 1 mole. So I got H plus left over, making the salt acidic, because there's more acidity left over. Okay. So from this discussion, I just want you guys to understand just how we determine the basicity or acidity of a salt. We're going to break them apart, okay, judging them by their reacting acid or reacting base, which one's strong, which one is weak, and whatever that's got left is the property of the salt. If we got more OH minus left, it's basic. More H plus got left, acidic. What about this salt yielded from strong acid and strong base? 1 mole versus 1 mole. 1 mole cancel out or neutralized completely. So that salt is neutral, like sodium chloride, right? So remember, sodium chloride and NaOH reacted with HCl, they're both strong, and 1 mole of H plus reacted with 1 mole of H minus. Boom, nothing got left. So that's neutral. Speaking of a salt yielded from weak acid and weak base, things become more complicated, because now we cannot just consider just how many moles of OH minus or how many moles of H plus produced, because they're both weak. So instead of us thinking about the moles of those cations and anions, we're going to check the Ka and Kb. Okay. Ka of what? Ka of a cation, because cation is an acid. Kb of what? Kb of anion, because anion is a base. Conjugated or not, they are acid or base anyway. So we're going to check out the Ka and Kb. If a Ka is greater than Kb, it's acidic. Solution should be acidic. If Ka equals to Kb, the salt is neutral. And in general chemistry, we have one particular salt that is neutral, made from weak acid and weak base. We call it ammonium acetate. That is a very useful compound, because this is a compound that gives us the pH of solution 7. If Ka is less than Kb, that means more basicity, so salt is basic. In our discussion in this class, we're going to focus on the first 3. The fourth one will be met if you're in a chemistry major later on in a more senior level of chemistry classes, a much more detailed discussion. So in my class, the first 3 is something that we need to understand. Okay, we need to know just how to determine the property of the salt. All right, the last example problem. It has two questions. Okay, so we need to predict whether the following salt solution are neutral, acidic, or basic, and even more, calculate pH. Let's look at the first one, ammonium bromide. First thing first, we need to know what kind of a compound this one is. Is that acidic? Is that acid? Is that a base? Or is that a salt? Because remember, we have our way to deal with weak acid. We have our way to deal with weak base. Salt is different from neither. So we need to know whether this is a salt. So how do we recognize a salt? Metal in the first element. Okay, so that is very important for us to realize. Metal or ammonium as the first element of the compound. Remember, salt is an ionic compound. Okay, so must have a metal or ammonium in the first place of the formula. So this is how we recognize it. For the acid, hydrogen must be in the first place. For the salt, metal must be in the first place. For the base, if that's ammonia, weak base. All right, so once we realize that both our compounds here are the salts, so here's its unique approach for the first two steps. Split the salt, so we know what the cation and anions are. So once from we have cations and anions, we determine what type of salt this one is by adding H plus OH minus. So here, for the cation, we add OH minus to make a charge to go away to form so-called reacting base. Okay, so ammonia or ammonium hydroxide is a weak base. The rest should be considered as a strong base, unless we are told otherwise. For anion, we add H plus to it to make a so-called reacting acid. Remember, we only have a 6 strong acid. The rest should be the weak acid. And by checking out strong acid or weak base, is this what the salt made up from? Solution is acidic because there's more acidity left. Remember, solution is acidic. Which K we want to use? Ka. A stands for acidic. If we have a Ka, fine, we use it. If we do not have a Ka, we solve for Ka. So here's how we're going to solve it. So this is the most tricky part. Sometimes we cannot use the K provided by the question. So for example, it is not the K that we're going to use. This one neither. Okay. So we need to find out what the property of this salt is. Acidic, Ka, basic, Kb. Sometimes question gives us the opposite K. We want a Ka, question gives us a Kb instead. We want a Kb, question gives us a Ka instead. Remember, Ka times Kb equals to Kw. So we need to do this little bit of conversion so that we can get a K we want. If salt is WASB, weak acid and strong base, remember salt is a basic because there's more basicity left. Basic means Kb. So once we have a Ka and Kb all figured it out, then we can use the AS table to solve the rest of the question, the rest of the math. But the first two steps is what is unique for salt. We cannot skip these two steps because first step, it will tell us what kind of salt it is. And from the kind of salt, we need to determine which K we want to use. Is that going to be Ka or is that going to be Kb? So let's put this into the action once we understand what our approach is. Ammonium bromide. Remember, first step, we split the salt so we can obtain cation and anion. ammonium bromide. So cation is ammonium, anion is bromide. For cation, we add OH minus. We understand it's going to be a weak base because it's ammonium hydroxide. Bromide, by adding H plus to it, is HBr. It's a strong acid. So the type of salt, strong acid, weak base, acidic or basic, acidic. If this is acidic, what K are we looking for? Ka or Kb? I hope you get it right, Ka. What K did we get from the question? Kb. So how are we going to transfer it? Okay, so how are we going to convert it? We use Ka times Kb equals to Kw. So Ka is equal to 5.6 times 10 to the negative 10th. This is the Ka we want to use. Okay, keep in mind, the solution of the salt is acidic. We use Ka, so for the reaction here, H3O plus must be the product. Okay, so that is very important. Do not give me OH minus, okay, because that's not the logic. All right, so once we have the acid association to write up, okay, so you may wonder what happened to this conjugate acid and conjugate base. Okay, so conjugate acid must be ammonium. And what is conjugate base? Ammonium. Okay, so that we can have a little bit of hydronium as a product. IH table. Okay, so we have initial concentration. We put a plus X under the hydronium so that we have plus X minus X for the rest of the species as a change in concentration. And we have equilibrium concentration, figure it out. And we're going to put those equilibrium concentration in expression of Ka. Remember, it's Ka. Okay, so put it in, which is equal to 5.6 times 10 to the negative 10th. Every time when I see an equation like this, I want the 500 rule. Okay, so I'm going to check out with that 500 rule. So initial concentration divided by Ka, so that is value is going to be much greater than 500, meaning we can take the X away. If we can take the X away, the calculation is going to be much easier. So multiply 0.25 for both sides, then we take the square root. So we have X equals to 1.2 times 10 to the negative fifth molar. What is this X stands for? If you still recall, hydronium or hydroxide. You're right, it's hydronium. So pH is equal to 4.93. Okay. So keep in mind, once we determine the type of the salt, it's acidic, we use Ka, we calculate for hydronium. All right, in our next question, so you probably recognize it's going to be the basic salt. So how do we know it's a basic salt for sure? We split the ions. We got it Na plus as cation, NO2 minus as anion. We add OH minus, make it sodium hydroxide. Everybody knows it's a strong base. We add H plus to NO2 minus, so we recognize it's a weak acid. How do I know it? Difference between the subscripts of oxygen and hydrogen is 1, so that's a weak acid. More base, less salt, or less acid type of salt is acidic. I'm sorry, basic. All right, so solutions are basic. We're looking for Kb. But here's the tricky part. Question gives us Ka. So what are we going to do? We're going to divide the Kb by this Ka so that we can have Kb figure it out. 2.2 times 10 to the negative 11th. Now that we have Kb, we write reaction. Remember, solution is basic, we must have OH minus as the product. Alright, so once we have the reaction, we set up ice table. We have initial concentration plus minus X for change in concentration. So we have the equilibrium concentration right here. And as to the next page, we use KB, right? So KB is what we have, and put the X in, and let's see if we can apply 500 rule to it. Apparently we can. So we take away that minus X. Calculation becomes much easier. So we multiply 0.20 on both sides, then we take a square root. So we have X equals 2.1 times 10 to the negative 6 molar. X again stands for OH minus. So we can get a POH. We are not going to get a pH directly. So we get a POH, and we subtract POH from 14. So 8.32 is the answer for pH of this question. All right, so that is